I'm Suzanne Eisenberg. I am a physics undergraduate at New Mexico Tech, and I worked at the SETI Institute RAU program over the summer with Dr. Vishal Gujar and Joel Ehrlicher on understanding the 1 to 10 gigahertz narrowband signal environment with GNU Radio at the Allen Telescope Array. So you guys have probably seen pictures of the Allen Telescope Array a lot during this conference, but the main goal of this telescope is to look for technosignatures. One of the biggest problems is that there's often a lot of interference from local technology. And so a big subject in radio astronomy is essentially figuring out how you can filter out those extra signals or document them to make observations easier. And that's what my project focused on. So I had three main goals. The first one was creating a radio frequency interference or RFI database for SETI searches, doing real-time RFI detection, and creating a process that was easy to repeat for future projects. So I did this primarily through GR Turbo SETI. You might recognize this as having been presented by a summer student 3 years ago at GRCon 2021. This software, or this out-of-tree block, is mostly designed in order to find drifting signals, so signals that change in frequency over time due to the rotation of the Earth, and also finding signals that are narrowband, and that's what we're primarily looking for in this project. So the updates that I did this summer were making this work for live signals. I essentially combined the block that did the buffer matrix that went into the main block with the actual processing block in order to make this work. So it finds the drift rate and it finds the frequency of hit, and this can also be used for other projects and is linked in GitHub later. So these are the main inputs. You take in frequency, time step, FFT, integrations, drift rate, and signal to noise ratio, and then it outputs for each integration a .dat file of the top hits with the frequency, drift rate, and index. And if you're interested in checking out this updated version, you can scan the QR code right here. So this is a very basic flow block that I used for taking the live observations. We essentially set up this system on the GNU Radio USRP and set the sample rate. We then did the FFT, and then we did the finding peaks and main data processing block. A lot of this project was sort of figuring out how to integrate the telescope with GNU Radio with the out-of-tree block and figuring out sort of what data rate we could take in without it overflowing the out-of-tree block and sort of balancing those things. And that's something that I would guess a lot of people at this conference are familiar with, that process of sort of working with data and your instruments and sort of figuring out how to integrate everything together. I found this to be a very valuable experience. As someone with a physics background, it really taught me more about how the radio aspect of the project worked. And so I enjoyed doing that this summer. We did 3 main types of test data for the actual RFI survey. You might recognize some of these from Luigi Cruz's talk, but the first one was a recorded data from Voyager 1 taken by the Green Bank telescope. This was in order to make sure that we were finding the peaks. We then did live data in the form of the TAN-1 lander on Mars, and so this was sort of pointing it at that and seeing if we could detect what we expected to in the right signal range. And then finally, we did an azimuthal survey with the wideband global SATCOM satellite to make sure that it was detecting things correctly across different azimuths. Due to the limited time from integrating everything together, I focused primarily on L-band, and so this is where a lot of technology is, but it's also really important in radio astronomy because it has the 1420 hydrogen emission line, which is a protected band, so we're hoping to not see a lot of RFI right there. Okay, well, the results are missing, but essentially we saw what we expected. The 1400 area was pretty clear, so people were doing a good job with those FCC allocations, and the 1600 area is very messy, as you would expect with the signal range. More importantly, we were able to get detections of drift rates, and so this means in future projects when we're trying to figure out the drift rate of the signal, we have a program to do that that's integrated with the Allen Telescope Array. So future work could include filling in missing azimuth and elevation values, doing varying times of day, expanding it to different bands, and also improving the real-time detection, allowing it to take in a bigger sample rate and process more data at a time. I would like to thank everyone from the SETI Institute, everyone from the Allen Telescope Array and Hat Creek Radio Observatory, everyone on the GNU Radio team, and the National Science Foundation for funding this research. The QR code links to the GitHub repository, and if you have any questions, feel free to reach out to me via email or LinkedIn. Thank you.